In this video, we'll talk about what exactly is Task Parallel Library and how different it is from our normal threading. So before I get into TPL and I start demonstrating TPL and I start explaining TPL, let's first try to understand, problems which revolves around threading. Now the whole point, we programmers use system.threading namespace, or we create thread objects, is because we want to run logics parallelly. We want to really run the logics parallelly, right? In other words, for example, now you can see here, I have a very simple function here called as run million iterations. And what this function does is it actually goes and it runs a for loop million times, and it does a simple concatenation, inside the for loop. And this method, run million iterations, I have, invoke inside a thread here called as O1. So you can see that I have created a thread object called as O1, and inside the thread object, actually I'm executing this method run million iterations. Now just a quick note here before I proceed. In case you have come to this video directly, or in case you do not have any idea of threading, what my suggestion would be to go and see the C# threading questions and answer videos, where we have talked about threading. We have talked about how to apply locks on threading, how to use mutex, semaphore slim, how to auto reset event, manual reset event, how to do thread pooling, how to debug threads, etc. So, before you go and see this video, I would suggest you to go and, once run through these videos over here, so that you can understand, what I'm speaking here about threading. So let's go back to our console application here. Now, what our expectation here is as a programmer is that, when this run million iterations method actually runs right inside this thread O1, our expectation is that, this run million iterations should utilize the CPU power to the maximum. So for example, now let's say that you have a P2 machine or you have a P4 machine, then my expectation would be to make this really multi-threaded. I would like that, from this million records, half of the million records should execute on core 1. Okay, and the half of the million records, logic should execute on core 2. And then finally, all the data should be concatenated inside this X and displayed. So my expectation here is that, when this run million iterations method actually runs, I would like that he should actually utilize my complete hardware power of my computer. But in reality, this does not happen. In other words, even though I have invoked this run million iterations, inside this thread over here, what happens is, this complete run million iterations for loop actually runs just on only one processor. So let me go and run the perfmon tool. Now perfmon, or I'll say performance monitor, is a tool which helps you to monitor different aspects of your computer, like, processor, memory, or probably any application from different perspectives. Currently, we are interested that, our application, how does it utilize all the 4 processor, right? So what I'll do is I'm going to go and, delete this default counter what we have here, right? Okay, so let me just go and expand this. So I'm going to go and delete the default counter here, and let me go and add counters which are important from the processor perspective. So currently we are interested to know that how much our processor time has been utilized, right? So I'm going to go and add all the 4 instances of my processor. So you can see 0, 1, 2, 3. Now each of these instances actually represents, each of our processor. Okay. So I'm going to go and add OK. So there it is. You can see now these, blue lines, red lines, yellow lines, and green lines, they indicate, all our processors. Okay. Let me also go and make these lines a bit thick, because, it is looking very thin over here. So let me go to the properties here and let me make the width a bit thicker so that we can see things in a more clearer way. Okay. So I'm going to go and apply to everyone here. Apply. Right. Properties and apply. So there we are. Now we can clearly see that, how our processors are actually loaded. Okay. Now let's go ahead and run our application, and then let's try to see that how these processors actually function. So let me go and run this application over here. Let me quickly switch back to my performance monitor, and let me clear everything, and let me start monitoring, what it is doing. Now you can see clearly over here, all the processors are not getting optimally utilized. For example, you can see this, this processor 1, which is indicated by the red sign here, it has been least utilized, or I'll say this, all these 3 processors have been least utilized. And look here, you can see this blue one, that is my processor 3, P3, core 3 has been utilized to the maximum. In other words, that is getting loaded more than any other processor. But what my intention was, or what I was thinking is, because I have spawned a thread, I was thinking that, all the processors should be optimally utilized, which is actually not happening, right? So in other words, when we say that we are doing threading, we are actually not doing threading. We are actually not doing parallel execution, but we are doing time slicing. What do I mean by that? Now, time slicing means context switching. So for instance, let's say that you have a single processor here, and on this single processor, let's say you have thread 1 and thread 2 running. So now, because we have only one processor and we have multiple threads running inside it, so what the processor does it actually distributes time between those threads. So for example, let's say it will first start with thread 1. At that time, it will not start thread 2. It will give its time to thread 1. It will execute some logic of thread 1. After that, he will make a switch to thread 2, and then it will start executing thread 2. And at that time, when he has switched to thread 2 and he's executing thread 2, he will not execute thread 1. After that, he will again stop executing thread 2 and switch to thread 1. So in this way, the processor actually switches time, or it actually distributes time between those threads, and it keeps switching from thread 1 to thread 2, thread 2 to thread 1. So in other words, actually multi-threading is not happening. Time slicing is happening. Context switching is happening. Also, one important FYI, if the processor is going to switch time like this between thread 1 and thread 2, in other words, it's going to do a context switch between thread 1 to thread 2 and then from thread 2 to thread 1, what it means is that probably, rather than increasing performance, it can probably decrease performance, isn't it? So in other words, what we really want is, we want thread 1 to execute on processor 1 and we want thread 2 to execute on processor 2. In simple words, this is what we are looking at. We want that in case it is a P2 machine, let's assume it's a P2 machine. Nowadays P2 machine, have become quite old, but let's assume that it's a P2 machine, and if I have 2 threads running, then I would expect, depending on scenarios, depending on how much loaded those processors are, I would like that thread 1 to be loaded on processor 1, executed on processor 1, and thread 2 to be executed on processor 2. If you remember the previous, loop 1 million times, which I actually looped, and when I showed you the perfmon counter, you saw that how only one processor was getting loaded. All the other processors were getting less loaded. In other words, even though I have executed my million times loop in a thread, multi-threading is not happening. Time slicing is happening, right? So in order to achieve parallelism, what we really want is, we want that our logic should get executed, optimally on all the processors, right? And if you look at today's world, right, the way, our computers are actually growing up, right, from P1, we are literally now come to P8. I've seen, 8 core processors, and it will probably go beyond that, right? So the hardware is, going to be available at a cheaper cost, and it's going to grow. So our application should have the capability to utilize that hardware, right? And that's what exactly TPL does. When you execute that for loop using Task Parallel Library, it will actually smartly go and execute those logic on the processors depending on who is loaded and who is not loaded. Let me show a demo of it. Now, in order to implement TPL, you need to first go and import this namespace here, system.threading.tasks. So you can see that the tasks, actually the TPL library actually belongs to the threading namespace, and that is logical because at the end of the day, task is an encapsulation over threading. Okay, so what we'll do is, so once you have imported this namespace, you are now ready to use the TPL library. So let me first go and comment that threading code. So I'm going to go and comment this. Now, in order to go and run this run million iterations 1 million times, what we can do is we can use the parallel.for from the TPL library. Now you can see that there are lots of flavors of parallel.for, but for now, very quickly to demonstrate parallelism using TPL, we will use the parallel.for. So you can see that, there are 3 inputs needed for the parallel.for method. One is first, from where you want to start the iteration. So that is 0 till where you want to go. That is 1 million times I want to go. And what do you want to run? The action. Okay. So that is run million iterations method, right? So I'm going to now go and run this run million iterations using the parallel.for method from TPL. Now my expectation here is that, this parallel.for, in other words, because I'm going to use TPL here, my expectation here is that this run million iterations should actually optimally use my cores of my machine. So for example, let's say that if I have a 2-core machine, then it should probably run 500,000 loops on core 1 and 500,000 loops on core 2. So I would like to see now optimal utilization of my processors of my machine. So what I'm going to do is I'm going to go and run this application over here, and I'm going to go and track the processor utilization using the perfmon tool, right? So let me go and run this. So I'm going to go and run this, and let me quickly go and jump to my performance monitor. Now you can see that there are amazing results here. If you remember, right, our previous perfmon data, all the 3 cores were utilized less, and there was only 1 core which was getting loaded. But look over here, you can see that all the cores are getting optimally utilized, and that's what exactly TPL is for. TPL, what it does is, it actually takes your tasks, okay, breaks them into pieces, and then says, okay, which of the processors currently are loaded less, and then he goes and tries to execute those logics on those processors, right? In other words, the big benefit of TPL over threading is it will actually execute or take the maximum usage from all the processors as compared to threading, where it had a affinity with the processor. Now let me rectify a statement, which I made previously. I said that threads have a core affinity. Core affinity means, once a thread actually runs on one core, it will always run on that core. Okay. But you as developers, you can write your own logic and you can make that thread run on different cores. But then you as a developer, you are responsible to check, which core is less loaded, then to go and divide your logical into logical pieces, right? And then execute those logic on those cores. And whatever data you get, you are also responsible to aggregate that data finally and then give it back as a result, to the program. Now, definitely that is a lot of work for a developer to do, right? To go and see, which cores are less loaded, and then go and query them, and then divide your task and then execute it, and then sync the data, etc. So TPL, encapsulates everything for you. So the first big benefit of TPL over threads is that TPL encapsulates multi-core execution for you. You just concentrate on your functions and methods to execute. All the other things, parallelism across cores, is taken care by TPL. The second benefit of TPL is thread pooling. Okay, now this video has become quite big over here. So what I'll do is I'm going to go and divide this video into 2 parts, right? So in the first part, we talked about, how TPL does multi-core execution. Now in the second part, we'll talk about how TPL automatically does thread pooling. Okay, so in case you are running thousands of threads, how it actually goes and, rather than creating those threads from scratch again and again, it actually does thread pooling. And with that, it actually also utilizes your memory properly. So in the second part, we'll see how TPL automatically does thread pooling. Thank you so much.